Good morning and good afternoon. Thank you, Conf42 and the organizers for providing me the amazing opportunity. And let me start with a brief background of the problem that you are going to talk about and how to solve that. So, in the biomedical research field, there are more than 1 million of research papers are being published every year. And if you take the citations of those research papers, it will multifold. Such tsunami of information is out there. When a researcher comes to do a research in that field, they first look for doing the literature review. That's the first step in any literature, any research process. When they attempt to do that, they have to go through these millions of records. Probably they can do a quick search in somewhere, but in spite of that, finding the relevant literature is very difficult, first of all. There may be a good literature out there that may be hidden from the researcher's search. That's also not good. There may be processing issues, like if they take into these millions of records into account, it will take forever to do that literature review. So, in sum up, I would say the researchers spend like a total of more than 80% of time just for doing this literature review. So this is the clear problem statement. This slide we already discussed about it, and our solution for this problem is intelligent AI literature agents. It contains four subdomains like domain adapted LLMs, that's LLM is large language model, advanced RAG system, it is advanced retrieval augmented generation system, precision NER system. NER is nothing but entity recognition for genes, proteins, and drug interactions, robust MLOps infrastructure. Let's go through this agenda. We'll first start talking about the MLOps architecture, and then we'll move on to Biomedical NLP Pipeline. We'll also talk about vector database scaling after that, and followed by monitoring and observability. And finally, we'll close with continuous experimentation and deployment strategies. MLOps architecture overview. So, when we talk about MLOps, everyone might have heard about this MLOps. It's a machine learning, how to operationalize the machine learning pipelines. So, it's MLOps is a critical part. Like just by developing the models, we cannot achieve everything. We have to implement it and make it production ready. MLOps is a crucial role in any machine learning lifecycle. So, effective MLOps, if you consider that, if you ask me to define an effective MLOps architecture, I would say that few components are necessary. The first one is containerized microservices. It's for modular scalability and versioning this model registry. So models keep getting updated, so we need to have it versioned in the model registry. Asynchronous processing pipelines for efficient batch citation updates, because in research community is very vibrant. The citation results and citation count, those things will vary every day. So we need to get the latest information to give the correct picture of that literature to the researcher. Clear separation of embedding generation from retrieval services, a real-time inference API layer engineered for sub-second responses, and dedicated evaluation environment to ensure rigorous scientific validation. So when we look at the biomedical NLP pipeline, there are a few challenges with the domain adoption, because biomedical is something which only few people who are really into the biotechnology and biology and healthcare, and those people are interested in, and it has lots of jargons and technical things, and not all of them will work on can understand these biomedical vocabularies, even the language and the researchers out there. So poses some challenges because the biomedical language is complex. It's because it's highly specialized vocabulary across sub-disciplines, entity relationship requiring domain expertise, like gene-protein interactions. That needs a domain expert to give good understanding to the researcher. Contextual meaning that changes across research areas. Need for continual updates as new discoveries emerge. Traditional NLP pipelines failed in this domain without specialized adaptation techniques. So, as a machine learning engineer or somebody who does the NLP on this biomedical data, not everyone can do that. They should have certain knowledge about this domain and the languages and certain level of understanding. Model training and deployment over workflow. So model training, it starts with data ingestion and cleaning and doing the exploratory data analysis. Those are typical steps in any machine learning. And once model is, you do all those things, you develop the model, you will have it checked with the test set and validation set, and you will have a working model. So imagine that it all happens and the data ingestion happens. Okay. And then you will go and training the pipeline. You will run the training the pipeline and evaluation framework. So we need to have a specialized metrics for biomedical accuracy with the domain expert review. And then we finally deploy the models. Scaling vector database for 30 plus million citations. So the operational challenges is like efficiently generating embeddings for massive document corpora and balancing recall against computational cost, managing seamless index updates. These are like issues with the operational issues with the vector embeddings. And with our MLOps solution to encounter that is asynchronous embedding generation pipelines with batch processing, hierarchical indexing strategies, and then read replicas with staged updates, optimized query caching. So these are the techniques to encounter those shortfalls or challenges, like I would say. RAG architecture and production implementation. There are lots of key components like domain-specific embedding models, multi-stage retrieval pipeline, citation network enrichment, and context window optimization. And with respect to performance metrics, we have to evaluate the things, evaluate the performance against baseline, I would say, to make sure that the performance has improved. Like sub-second query latency, 90% accuracy in the entity recognition, and citation relevance score is coming up more than 85%. Such KPIs are really important when evaluating performance. It's not about just doing the things. We also need to make sure that we are doing the right thing and getting the right expected results within the stipulated time. So the final one is, reduction in the researcher literature search time. Monitoring and observability framework. So once we deploy the model and the data may change, it's evolving, the model which work efficiently while we implement it first time may not work over the period. So we need to constantly monitor the models and then do the fine tuning. So model performance tracking, scientific accuracy validation, and user interaction analysis, they are really important. And we have to, once we are done with the work, we cannot say that it's all done and we don't need to revisit. We have to come back again, and we have to have a certain metrics to evaluate every time and make sure that if it's derailing or maybe deviating from the desired expected outcome, then we need to intervene and fine tune the model or maybe enhance the ecosystem to produce the right output. Real-time monitoring dashboard. Our custom monitoring solution provides both ML engineers and scientific stakeholders with visibility into model drift detection, citation accuracy, system health and performance metrics, user query patterns and success rates, resource utilization and scaling triggers, ARB testing performance comparison. Continuous experimentation methodology. We have implemented A/B testing framework that balance experimentation with scientific reliability. So it enables targeted cohort testing by research domain, measures both technical metrics and research outcomes, and provides statistical confidence for biomedical applications. Supports multivariate testing across model components. If this approach has yielded 80% reduction in literature search time while maintaining scientific rigor in results. Infrastructure scaling patterns. So we have to have a baseline infrastructure. Its core components sized for average load with 2 times redundancy. Elastic scaling layers, auto scaling inference endpoints based upon query volume, and scheduled scaling events. Predictive scaling for known search patterns, like especially maybe sometime towards academic term, then if you observe that the demand increases, we may have to plan for the scaling in advance. Specialized compute, GPU allocation for embedding generation and inference. Our infrastructure scales efficiently across both batch processing needs, real-time query patterns. So this is really important while making sure that we are not doing less or more, we are doing the right thing. Key MLOps learnings from biomedical AI. So we saw that we have to integrating domain expertise. That's really important. Without the involvement from domain scientists, it's difficult to do a right MLOps without the domain experts' help. Developing scientific validation pipelines. That's also another important. We cannot just be sure that the performance has increased just because the time to search has come down. We have to also measure based upon the other scientific variables and KPIs. Enabling continuous corpus updates. This is really important. Corpus is increasing, so we have to keep up to date for the latest and greatest information. Prioritizing explainability. Biomedical research application necessitates significantly higher transparency and interoperability standards compared to consumer AI system. And with that, I am concluding, and thank you for this opportunity. Thanks a lot.